What I'd like to do is, before I begin my lecture, since I caused a little bit of confusion the last time regarding the intrinsic semiconductors and the position of the Fermi level, we got into a small argument about the sign and the magnitude of factor there, which involves the effective masses of the electrons and the holes. Basically, what I said was correct, that the hole effective mass is larger than that of the electron effective mass, and that equation then becomes a very small number. Actually, what I said was correct. Probably I might have said that there is a significant difference between the effective mass of the hole and that of the electron, but that's not always the case. But even if that is very different, I'll show you some magnitudes to give us an idea. We will still find that the whole factor that we have there, that minus 3 by 4 kT, the natural log of effective mass is the ratio, is still a rather small correction to the rest of those terms. So let's take a look at that so that we can clear up that confusion before we go on. Just to illustrate the point, we've got the equation for the Fermi level in the intrinsic case was EFI is equal to EV plus half EG minus 3 by 4 kT, the natural log of ME star by MH star. This was the equation that we had trouble with. How come, the log of this number won't be a large thing and so on. Actually, unless it's very significantly different, it's not going to be all that much. Plus, we have to remember that this term, kT, in terms of EV at room temperature is only 0.025, 0.026 EV. So you're multiplying a fairly small number by 0.026 by 0.75, and I'll show you what happens. So let's begin with some idea of what the effective masses are. Normally, we express the effective mass as a ratio like this. Okay, compared with the free electron mass, what would the ratio be? So I will give us for both the electron and the holes a flavor of a couple, 2-3 different materials. Let me begin with diamond or carbon, basically. And in that case, the whole mass is given as 0.25, and that for the electron is 0.2. They're not significantly different. They're very similar in that. And then if you look for the more familiar case of silicon, this is 0.29, and for the electrons it's 0.26. So still we don't have much of a difference. Then we come to compound semiconductor like gallium arsenide, then we have 0.082. We can see that the whole mass is very light there, but so is the electron value, significant difference compared with the free electron mass. And we'll see how that plays into mobility. There are significant mobility differences between these materials. And then we have indium arsenide. Even in the case of gallium arsenide, while the numbers are small, they are relatively close to each other. In the case of indium arsenide, we have 0.40, 0.23, almost half of the other. So we can take these 4 cases and look what might happen to this term, and how would that change the idea that the Fermi level is approximately located half EG above EV. That's what this equation means. How much of a shift is there in the intrinsic Fermi level once we take into account these ratios? Okay, so for each of these materials, we'll take a quick look. Excuse me. And we can see for the case of diamond that this ratio, let me write that on top here, we'll do that for each of them. For diamond, that ratio turns out to be 0.223. And for silicon, it's minus 0.109. For gallium arsenide, it is minus 0.202. And for indium arsenide, here we see that because of the significant difference in the masses, it's a little bit of a larger number. Now remember, this is only the bracketed term there. We still need to multiply this by 3/4 kT times this number to get the actual change from the middle of the band gap. And when we do that, kT, as I told you, at room temperature is 0.026 eV. That's something we saw earlier, a very convenient thing. So 0.026 times 0.75 times this. So the effective correction factor becomes a positive shift. Remember, in this equation we had the negative sign, and all these are negative. So we've got a positive shift. That means a little above the middle of the band gap. And these are the orders of magnitude, the changes. 0.0043 eV, 0.0021 eV, 0.0039 eV, 0.0107 EV. And when you look at it, it's interesting that, as I said, except for indium arsenide, where there is a significant difference in the hole and electron effective mass, the change that is there is so insignificant. It's in the third place of decimal. Only in the case of indium arsenide do we see a change that is in the second place of decimal. And by comparison, if we look at what is the band gap value, 5.47 EV, 1.12 EV, 1.42 EV, 0.36. Okay, indium arsenide is a very narrow band gap material. And so in the other cases, half the band gap, 2.7, whatever it is, from there it is shifted by only about 0.0043, that additional correction. For those of you walking a little late, we're still looking at that argument that we had about the effective masses, if you recollect that it should be a very large change. And what I'm showing is that if we put some actual values and look, that the change is not significant. It is only shifting it by about these numbers. All right? Because the effective masses for hole and electron in most of these materials are relatively close to each other, except in the case of indium arsenide, and where there's almost half of the other. And that's why we see a more significant shift in the case of indium arsenide. Even then, it corrects, say, from 0.36 to 0.37. I'm sorry, 0.18 to 0.19, half the band gap. Remember, we are talking of where the Fermi level should lie. So if this is 0.36 is the band gap, so this is 0.18, and what we are saying is that if we account for this correction, it will be 0.19. Whereas in the other cases, the change is even more insignificant. It's in the third place of decimal. Okay? So I just wanted to clarify that. I think I wasn't very clear. The main point I made was correct, but I wasn't able to explain that properly to you in the previous class. So I hope that puts that question to rest. What we were left with, I think the last time, if you can help me, I think what I did was that we checked out, I gave you some equations for calculating the Fermi level in the N and P type. Is that right? Correct me if I'm wrong. Or was it that I thought about compensation? I don't quite recollect. What were the last equations that I gave you? Fermi level in N and P type. Okay, very good. Now what we'll do is continue as for the intrinsic case. So far we've looked simply at the material in equilibrium. What happens if we connect it to a voltage source? That's the question, very similar as to what we did for the intrinsic case. We're going to connect this to a voltage source. And when we do that, this is, say, an N-type material. All right? So the carriers, plenty of them that are there in excess, are the electrons. Now, in response to this applied voltage, the electrons will drift in this direction. Okay? And we'd seen earlier then that the potential drop that we have, if we look at it as a function of x, will look something like this. V as a function of x will look, the potential is going to drop across the material from this side to this side. We get the potential drop. And the implication why we have to draw it linearly is because if the field has to be uniform, as we had earlier, then we have to draw it as before that if V can be expressed as AX plus B, the same argument as before, then the epsilon or the field, which is minus EV, would then be a uniform term. Okay? That was the basic argument we used even in the intrinsic case. And what this means then is that in terms of the diagram that we just drew, I could probably draw it, no, draw it afresh, is that while the potential is dropping this way, the field is dropping the opposite way. That's the basic, not the field, I'm sorry, what did I write here? Excuse me. The potential energy is minus EV, not the field. Field is V by X. but potential energy drops the opposite way. So that means we are ending up with a situation where the material to the right has got a lower potential energy than to the left. And as before, what that implies is that the band has been tilted in one direction. Okay, that's the valence band, conduction band, and the whole thing is tilted downwards. In this case, we're not going to worry about the holes because the most of the conduction practically is taking place due to the excess of electrons. But again, as before, these holes now find a gradient down which to drift. And so that is what is our source of current. As these electrons move, they are replenished from the source, and so we get a current in the circuit, except that this time the current is dominated by electron flow. As we saw, sigma was only related to the n E mu of the electron side. That's all. The P part of that conduction we leave out, unlike the case for intrinsic case, because n is much greater than P. So this is just a simple statement there. Now what I want to do is, so far in all these statements we have not worried about the role of temperature as far as the conductivity is concerned, other than to suggest that the ionization or the excitation of the donors or acceptors is a temperature-dependent phenomenon. I just mentioned it that most of those equations would have to be modified if we go to low temperatures, because most of the places we have assumed complete ionization. In other words, we have assumed that n is equal to nd in all these equations. But I mentioned in both these cases that n is equal to nd or p is equal to na, as the case may be, that when we go to extremely low temperatures, these equations don't hold good anymore. We have to take into account the fact that only some of the donors and acceptors have been ionized. So what we want to do is to look at the temperature dependence of conductivity in an extrinsic semiconductor. Excuse me. That's pretty much what we will cover today. We'll look at different aspects of this. Now we know that sigma depends on two things. What are those? Well, okay, it depends on temperature, but if you look at the equation that relates sigma to carrier concentration and mobility and things like that, we have, if we consider there is the carrier concentration, Ne mu or Pe mu h or whatever it is, right? So two things are important: the carrier concentration in an n-type, it's n, or P, as the case may be, and the mobility term. The E is a constant there, so I don't need to bother about it. So in order to understand what is the temperature dependence of sigma, what I would like to know is how does n vary with T, which in this case earlier we haven't really bothered much about it other than to believe that everything is ionized. And we will also want to know, does mu, the mobility, depend upon T? We have some inklings about it when looking at the metal case, you know, that the scattering depends upon the atomic vibrations and things like that. And so we have some idea that there should be a temperature dependence for this. And as I mentioned, ionization is also a temperature energy dependent term. So if we can understand these two terms, we have a handle on understanding the conductivity's temperature dependence. So let's begin with carrier concentration. We'll consider an n-type material. Which has been doped with Nd donors per centimeter cube. And we have doped it enough, as we said earlier, such that Nd is much greater than Ni. In other words, the properties are now dominated by the donor behavior and not by the intrinsic behavior of the material. And what we are going to do is to begin at extremely low temperatures and try to track how these donors get ionized and what might be happening to the material as a whole in terms of both the ionization of the donors as well as the thermal generation of electron-hole pairs. Now, as we might suppose, at very low temperatures, the Ni, which is related to the thermal generation, intrinsic, what would we say about it? Would it be large, small? Small, right? Because we are, in this case, we are having to excite across the band gap. So at very low temperatures, Ni is very small, negligible. And we have to ask, what about the carrier concentration due to donors? Would they also be very negligible? It's also small or none, or n is equal to nd, or? It will be smaller than nd. Okay. You have to always be careful about these words like which I use at very low temperatures. What does it mean? Okay, for different semiconductors that means different things, obviously. So it's simply in this statement order of magnitude. We're talking of something that is very, very low energies, thermal energies available. And since ionization is a thermal process, hardly enough energy is there to excite the ions to go to a higher temperature. Even though this is the energy gap across which they have to jump, because that's the donor energy level. Excuse me. Conduction band, valence band. So this we saw is out of the question. But at very low temperatures, this jumping also from the donor level to the conduction band, which is what we mean by ionization of the donor, is also pretty small, insignificant. So conductivity is very low because there's hardly any carriers to get excited. But then as we, Nd practically not ionized, is what we can say. Now as we increase the temperature gradually, the first thing that's going to happen is that more and more donors are going to be ionized, because this will require a lot more energy. So initially it's the donors that will get ionized. So on increasing the temperature, we will find that the carrier concentration increases because donors are getting ionized, and this can be expressed by half Nc Nd to the power half exponential minus delta E by 2kT. There's no major magic involved here. It's a very similar expression to that for the intrinsic case. As an aside, recall the intrinsic equation that Ni is equal to Nc Nv to the power half exponential what? Eg by 2kT. We had this, right? And you can compare these two to get a feel for the major differences being that we are using Nd instead of Nv, because it is the number of electrons that are sitting in the donor level that counts here, not the density of states in the valence band, because we are exciting from the donor level. And this half, if you recollect, we said that the statistics of occupation of the donor level was different from that of the valence band, for example, because only a single electron is going to occupy. Very good, you remember something there. Only a single electron is going to occupy. It could be of either spin state. And so this half, we had a probability distribution for donor levels, which included this half term. And so that also ends up here. So other than that, there is no major difference. And instead of the band gap here, we are going to use delta E, where delta E is nothing but Ec minus Ed, or this little gap over which it should be excited. For the intrinsic case, we had to consider Eg because the excitation is across the band gap. In this case, the excitation is from here to here. So accordingly, the equation has been modified to include a delta E, which is simply the difference between the donor level and the conduction band. So at a fairly low temperature still, and as we increase the temperature, it's going to follow a temperature dependence like this. Now remember, T has got an exponential minus 1 by T dependence here, but there is also a T dependence for this. 2 pi me kt to the power stuff we have there. Okay? So that is the temperature dependence at relatively low temperatures. Now as we go on increasing the temperature, what will happen? Incidentally, this region is known as the ionization range at these low temperatures, which we are talking about where this equation holds good, is referred to as ionization range. It's the range in which donors are gradually getting ionized. Okay? And as we increase the temperature, what would we say is going to happen eventually? I'll give you a concrete example to think about. I put in 100 arsenic atoms into 1 million silicon atoms or whatever it is. So low quantity. And then I'm going on increasing the temperature. Initially, none of the arsenic is excited. And then as I increase the temperature, 1, 2, 3, they're getting ionized. So electron concentration is going on increasing significantly. What happens at some point? Saturation, very good. I have ionized all 100 of them. So till I have another mechanism of generating further electrons in the conduction band, there's going to be no other source. And the only other mechanism available at this point is what? Thermal generation across the band gap. And we haven't as yet got to that point. The temperature is not high enough for that to take place. So what will happen is that N has become equal to Nd. I've ionized all my donors, and that does not change for a while. There's no temperature dependence because Nd doesn't depend on temperature. Okay, it's a fixed number. So now I'll have a flat region, what we call saturation. As that was called ionization, this is called the saturation region. All right? So this situation continues till we get to a temperature, at still higher temperatures, when band-to-band thermal generation can take place. Okay? At still higher temperatures, we get band-to-band. And now the conductivity is going to be dominated, I mean the electron concentration is going to be dominated by the thermal generation of electrons, for which we already had the equation that I wrote earlier. Ni is equal to Nc Nv to the power half exponential minus Eg by 2 kT. Okay? So I've got now three regions roughly. One at low temperatures where the dependence is on how the ionization of the donors is taking place, which we called the ionization range. The second area where all the donors have been ionized, and so it's saturated. Another word for this is called the extrinsic region. The properties are predominantly due to the electrons that have been introduced due to the doping. And then we have a third region where now intrinsic generation of thermal of carriers has taken place, and we are generating now electron hole pairs. For every electron that is now put in the conduction band, a hole is created, which was not the case in the earlier case. And this area is then referred to as the intrinsic region. Okay? So we can make a plot of all this. The three areas, one in the early stage where N is dependent on the ionization of donors. It's got a temperature dependence T here, exponential minus 1 by T, and an NC's temperature dependence. Here we've got no temperature dependence. And then we've got a third region where again the temperature dependence is a minus 1 by T, and again NC and NV have temperature dependencies. Okay? That's the scenario we have. I'll just mention in passing that in this region here, what we call the extrinsic region, p-n junctions and things like that are operated in this region. Because over a range of temperature, we've got a flat profile. There's no change in the carrier concentration. Okay? So that's where we operate p-n junctions in that region. And we can control what is that temperature range over which it will be showing this characteristic. There's going to be two temperatures of importance to us. One that I will call Ts, at which point we've achieved this condition, and one temperature called Ti, at which point we've gone into the intrinsic range. So between Ts and Ti in temperature, we are going to have N is equal to Nd, a flat profile, and that width can be varied. That temperature range can be varied depending on how much we dope and what is the band gap of the semiconductor and so on. But that gives us some margin over which we can operate the device without changing the carrier concentration. So let's plot the same kind of equations would apply for a p-type incidentally. But let's make a plot then of carrier concentration versus temperature. Actually what we normally do is to plot the natural log of N versus 1 by T. Why would we do that? And so if we do that, what would we expect? Linear, right? So in this case now, this has also got an exponential 1 by T, minus 1 by T. Here also we've got an exponential minus 1 by T. So two linear regions. And then we've got something that doesn't have a temperature dependence. So a flat region. Slope is 0. Now, it's not going to be strictly linear because of this additional temperature dependence that we have for this. and for these two. But the exponential term is far more dominant than these terms. So essentially it will look like a straight line, but we have to keep in mind that strictly speaking, this also has a temperature dependence. NC also has a temperature dependence, and in this case NC and NV also have temperature dependencies. So what we will expect is two linear regions separated by a region with a flat slope. But the slope of both these linear regions are now going to be different, because in one case it's delta E and in the other case it is Eg. So here now I have a method for determining, first of all, how shallow or what is the energy difference between EC and EC and ED. The donor ionization energy I can experimentally determine by determining carrier concentration versus temperature, measure it, and then I make a plot like this, and in the lower temperature region, the slope of that is minus delta E by 2K, from which I can calculate how much energy does it take to ionize a particular donor. We can do this for different donors and see which is the most suitable one that we have. And the other region will give us then Eg. The slope of it will give me minus Eg by 2K. So here we have an experimental technique to determine both Eg and the ionization energy. The slope will look, the curve plot will look something like this. Excuse me. We start from the low temperatures. This is the low temperature. We've got something that has got a small slope up to a certain temperature, and then there is the flat region, and then usually we'll see a much sharper. Now I draw this much sharper because Eg is much greater than delta E, obviously, right? Delta E is a very small number, 0.0 something, it's in milli electron volts, whereas Eg is of the order of electron volts. So that's why the slope will be very different. Now here we have our three regions. We can roughly take the temperatures. What would this be? This is 1 by T, but what would that temperature be if you look at it on the temperature scale? 1 by Ts, very good. Okay, and correspondingly then we have here 1 by Ti. So this range here, whose slope is now minus delta E by 2K, is my ionization range. Gradually I ionize, concentration goes on increasing, log scale, so rapidly increasing. Then it saturates, and then I increase further, and at that point here now the slope is minus Eg by 2K. So we've got ionization, saturation or extrinsic region, and the intrinsic region. I've had some very interesting experiences with data that look like this. I will probably use it in another lecture just to caution about some of the dangers if we have the time for it. I don't know if you have time. But how easy it is to get misled when we do actual measurements. Most of you will not do it, so I may not have the time to go into it. But this is a very useful curve. So here we have now one of the terms that we are looking for, the temperature dependence of the carrier concentration over the whole range that we can possibly study. So the next thing that is of interest to me, or before we get to the mobility, I want to discuss one more thing. We can also express, again, Fermi level, okay, in terms of ED and ND. We had an expression in the last lecture I closed that the extrinsic Fermi level minus the intrinsic Fermi level. Right? That was the equation I gave, is equal to KT natural log of something or the other, right? Now in this case, we want to know with respect to ND and ED, what is the Fermi, where is the Fermi level? In other words, in an extrinsic case, this is my intrinsic Fermi level. That's EC, that's EV, and this is the donor level. The question is, where does the Fermi level lie with respect to the donor level? All right? What the equation I gave you earlier was with respect to the intrinsic Fermi level, where does it lie? And we can use a similar approach to show where the Fermi level will lie. we have the general expression n is equal to nc exponential minus EC minus E Fermi level by kT for the electron concentration. In the low temperature range, we also have n is equal to nc half nc nd to the power half exponential minus delta E by 2 kT. I think I need to change that, right? And this delta E we can express as EC minus ED. So in the low temperature region, we can equate these two equations. This is a general expression in terms of Fermi level. This is another expression in terms of the donor level. And when we do that and solve for EFN, we get it's equal to EC plus ED by 2 plus half kT ln nd by 2 nc. All right? That's when you work through this and solve for EFN, we will get this equation. So at very low temperatures, where would the Fermi level be? Obviously, the kT term is going to be insignificant. So it's EC plus ED by 2. Where is that? Between, it's the average. It's between EC and ED. Okay? So to start with, at low temperature, so now if I'm going to make a plot of Fermi level versus temperature, you got ED, I'll just draw it bigger so we can see it. Now here I have the case that to start with, so this is going to be plotted Fermi level versus temperature. Okay? So temperature is increasing in this direction. How does Fermi level shift? Well, at very low temperatures to start with, we know, we just saw that the Fermi level will lie midway between these two, between EC and ED. Actually, as temperature increases, there will be a slight increase in it because of the temperature dependence of this term here. But basically, as we start ionizing, the Fermi level will fall. Okay, we'll leave it at that point. Now, as I go to extremely high temperatures, what has happened to the Fermi level? Where would it be? What is it? Think of the temperature dependence of all what we've talked about. Or basically EFI, right? I mean, slightly greater than half EG, which is EFI. So eventually at high temperatures we have, it will be at EFI itself. So the temperature dependence will follow something like this. It starts between EC and ED, then comes to ED, drops below ED, and eventually at some temperature where it becomes intrinsic, then it becomes the same intrinsic Fermi level. Now intuitively you have to think of this. What does it mean that the Fermi level is sitting here? Think of the definition of Fermi level at temperatures greater than 0. How did we define Fermi level? Probability of occupation is half. That was the basic definition we had, right? What's the occupation level of ED at extremely low temperatures? Yes, temperature is very low here. What is it? Well, it's all sitting there. It hasn't been ionized, right? What's the probability of occupation of the valence conduction band? 0. Fermi level is where the probability is half. So just intuitively thinking in terms of the definition, we could have guessed at where the Fermi level would be at very low temperatures. Okay? And then as it's getting ionized, more and more are going into the conduction band. Accordingly, the Fermi level is dropping till beyond a point we've entered into the intrinsic range, and now it is dominated. It's back at the original, about halfway in the band gap. Okay? So you can use simple intuition to try to arrive at some of these without looking at the mathematics of it. The mathematics helps us to confirm the intuition, that we can arrive at it in a very simple way. All right, so we've got now electron carrier concentration versus temperature. The next thing we want to know is how does mobility change with temperature. Now, there's two things that we'll look at here, not only the temperature dependence, but mobility has also got another dependence we might guess, namely impurity concentration dependent. Remember, mobility is fundamentally about scattering. So all the possible causes of scattering will affect mobility. And we saw that the fundamental thing in the case of the metals was what? Phonon scattering. So we will expect phonon scattering to be important here, particularly at high temperature. So we will look at the temperature dependence of phonon scattering. But the impurities also play a role because when they get ionized, there is an interaction between the ions and the electrons, as we will see. So there's a scattering due to ionized impurities. There are other mechanisms also which we won't go into, but we'll consider these two major mechanisms of scattering. And then the question will arise, does this also have a temperature dependence? All right? So we'll look at that in two stages. We'll start with the temperature dependence, and then we'll go the phonon scattering dependence, and then we'll look at impurity concentration dependence. So let's begin with the idea of phonons, phonon scattering. We've seen earlier mobility proportional to tau, the mean free time between scattering events. Right? This is something we already saw. And we had an expression for mu is equal to E tau by me star. When we were looking at metals, we went through all this. Where tau was expressed as 1 by S VTH NS. We had seen a scatterer atom that is vibrating, and S is the area of it. So S is the cross-sectional area of the scatterer. VTH we saw even the other day was the thermal velocity. And then NS is the number of scattering centers per unit volume. Per unit volume. All right, this is the general expression we have. Now what we're interested in is for both the phonon scattering as well as for impurity scattering, do any of these terms have a temperature dependence? That's the main idea that we're going to explore. Let's take S. The area is pi a squared for phonon scattering, where A is the amplitude of vibration of the atom around its mean position. This is something we had seen earlier. So for phonon scattering, S is equal to pi a squared. And we also saw there in that, I will not go through it again, you can go back to your notes, that a square is proportional to T in such a case. If you'll go back and look at metals, you'll find this over there. So what we can say then is that S is proportional to T.
So A square is
Yes, that's what I wrote here. A square is proportional to T.
No, that's what I was asking. A square is proportional to T or A is proportional?
A is proportional to root T, I think, in that equation. Go back and see your notes. Okay, so A square gets proportional to T, and that's why S becomes proportional to T. I've just written it in terms of A square. What I gave you in the notes, if you go back, maybe that A is proportional to root T. Therefore, A square is proportional to T. That is why I think it is causing a confusion in your mind. Okay? But S is proportional to T as a consequence. So we know for these terms here, S has got a temperature dependence given S is proportional to T. The next thing that we need to worry about is the temperature dependence of VTH. And what we saw is that for these electrons that are there in the conduction band, we can treat it like a gas, essentially. And we calculated that we can take it as 3 by 2 kT is their thermal energy, which we equated with half me star V TH, from which we got that VTH has got a T to the power half dependence. We did this the other day. So S has got a T dependence, V has got a T to the power half dependence. Does N have any temperature dependence? The number of scattering centers? Remember, we are talking about phonon scattering, primarily from the vibration of the atoms. Would you expect it to have a temperature dependence or not? Do the number of atoms generally in the solid change with temperature? I mean, concentration, number when we say per concentration, per volume. No, right? So obviously this doesn't have any temperature dependence. So now we have this one's temperature dependence and this one's temperature dependence, and we can go back to the earlier equation and say that tau, I'm going to put in a L subscript there to indicate that it is related to lattice scattering or lattice vibrations, phonons, to distinguish it from another case, has got a proportionality that would be given by, we saw it 1 by the S's temperature dependence times the temperature dependence of VTH, and then N didn't have a temperature dependence. So we can then write that tau L is proportional to T to the power minus 3 by 2 or T to the power minus 1.5. Okay? So accordingly, since mobility is proportional to temperature, mobility that is due to lattice scattering then is also proportional to T to the power minus 3 by 2. So lattice scattering has a T to the power minus 3 by 2 temperature dependence. One aspect of it we've got. The other thing is due to impurity scattering. Now what we have to see here is why should an impurity cause scattering, and I briefly mentioned it. It is due to the fact that when the impurity donor is ionized, or the acceptor is ionized, it leaves behind a positively or negatively charged core. And the electron that is then passing through will get attracted or repelled by that ionized core. So it is basically an electrostatic interaction between electron in motion and the ionized core. All right? So it's something like this. If I've got the ion here and the electron is coming, if it's far enough away, that interaction is too weak, the electron just passes through. Okay? As it gets closer, it's attracted, so it's moved away from its path. Or the opposite might be the case if it was a negatively charged acceptor ion, in which case the deflection would have been in the opposite way for acceptors. This is the basic idea that we have. Now we can write the electrostatic interaction, because we know it, the modulus, depending on whether it's acceptor or donor, it doesn't matter. We can write it as E squared by 4 pi epsilon naught epsilon r squared, where r is how close is it to that particular ion, this radius term there. Now the question is, we have an expression for potential energy, the interaction there. Does the kinetic energy have a temperature dependence? Kinetic energy, does it depend on temperature? Yes. Right? It had better, we just used it. Half m squared is equal to 3 kT kind of idea we got there. So there's a temperature dependence for Ke. So instead of looking at it in terms of distance here, we can also think in terms of, all right, if the electron has got a very low kinetic energy, what is the chance that it will get deflected? More. And if it has a higher kinetic energy, the chances of deflection are low. Right? So from there we can try to think in terms of a temperature dependence for the scattering. The higher the temperature, the higher is the average kinetic energy of the electrons, the lower is the scattering due to ionized impurities. Ionized impurities, not the total impurity concentration, ionized impurity concentration. Okay? So that's the idea we get, that as T increases, kinetic energy is increasing, and therefore the ionized impurity scattering will decrease. broadly speaking like that. And we can say that for a given temperature, the kinetic energy will be given to us by 3/2 kT. We saw that earlier. There will be some critical radius for this equation that we have here. Where did it go? Here. Which we can write RC, where these two terms are equal. So we can equate then is equal to E squared by 4 pi epsilon naught epsilon r RC squared. And from that we can solve for RC is equal to E squared by 6 pi epsilon naught epsilon r kT. All right. The point of calculating RC is that now, same way as I had S is equal to pi a squared as the scattering area for the phonon interaction, for the ionized impurity now, I have the temperature dependence of S given by pi RC squared, for which we have a temperature dependence, namely 1/T. So in the case of thermal scattering, it was S was proportional to T. In this case, S is proportional to, because, I'm sorry, 1/T squared, very good, 1/T squared. All right? So this is the first part of what we have. Now when we look at thermal energy, the velocity, just as before we have the same T to the power half dependence. And so we can write then that tau I, which is equal to 1/S VTH Ni, where now I'm making this the scattering time due to ionized impurities. And looking at the temperature dependence, we can say it's proportional to 1/T to the power minus half, minus 2, which is this dependence. Okay? And V has got a T to the power half Ni. We leave Ni for now. Remember, I asked you the question whether the number of ionized impurities depends on temperature. So this also has a temperature dependence. It also has a dependence on how much I dope. So even for a given temperature, if I put in more donors, it will have a role in changing tau I. So we can summarize this by writing it is equal to T to the power 3/2 by Ni. Okay? Tau, impurity scattering, is proportional to T to the power 3/2 by Ni, from which we get mu due to impurity scattering is proportional to T to the power 3/2 by Ni. Actually, it becomes pretty complex because, as I said, Ni has its own temperature dependence, which was exponential minus 1/T dependence. How the donors are getting ionized. So it gets pretty complicated when you take that into account below Ts. Once you are at Ts, then it's not changing with temperature. So in the saturation range, we don't have to worry about the temperature dependence of this term here. Okay? So mobility then is proportional to T to the power 3/2 by Ni. Now I've got mu L and I've got mu I, and how do we determine the total mobility? You've heard for resistivity we use that Mathieson's rule. Yeah? Very good. 1/mu due to electrons is equal to 1/mu L plus 1/mu I. So the overall mobility is determined by the lowest mobility, according to this equation. Whatever, we'll combine all the mechanisms, and the one that has the lowest mobility at any given temperature, that's going to be the overall mobility determining term. Sort of like the weakest link is the one that determines what is the overall mobility. There are actually other mechanisms which we are not considering. So the picture we draw will not be strictly accurate. There's other things. For example, in a compound semiconductor, we've got something called, in an alloy and things like that, we've got alloy scattering. Okay, different types of atoms it encounters, so the scattering is different. Then there's stuff called intervalley scattering, when we look at band gaps, the band structure. Then there's deformation potential and so on. There's other terms. And in some cases it applies, in others it doesn't apply. So, and mostly they don't really significantly influence the case. So what we can do is to ignore those for the time being and focus just on these two. And when we do that and we plot again mu versus t, we'll take a log-log plot. Basically it's a log mu versus log t on a log scale if you look. I had plotted here, or maybe I didn't plot. No, I didn't plot. If we do this and we plot for each of those cases, one has got a t to the power minus 3/2 dependence, ionized impurity. Forget about the exact shape and all that, I'm just drawing. Let's call that the mu I with a t to the power minus 3/2 dependence. And then there'll be the mu L, which has got a t to the power, I'm sorry, t to the power 3/2 is for the positive one, is for ionized. And then mu I has got, what am I saying, mu L due to phonon scattering is proportional to t to the power minus 3/2. These are the two curves. And basically to know the overall mobility, we add it up sort of point by point, one by this thing. And the overall mobility curve looks like this. Something like this. As a function of temperature, the mobility looks like this. Okay? Now if we take into account other scattering mechanisms, maybe there's something that has got a temperature dependence like this, one other mechanism, and so on. And so the exact shape will be changing a little bit, but overall we see that there is a peak mobility given to us because of the combination of these two factors. I'll just give you a simple set of numbers to give you an idea of mobilities in different materials, and then we'll stop because I don't have time to combine it together. But you can see that if I have ionized impurities in lower, as I reduce the donor concentration, slope remains the same, but this shifts. So for lower and lower donor concentrations, it will be shifted this way. Effectively, what that means is that the peak is moved to lower and lower temperatures. Okay? So we'll combine this in the next class. I'll simply give you a few ideas of room temperature mobility so that you can have a feel for these numbers. For silicon, it's something like 1500 centimeters square per volt second. Gallium arsenide, it is 8,500. For indium arsenide, 33,000. For indium antimonide, it's about 80,000. These are the electron mobilities. And for holes, correspondingly, it's about 450, 400, 460, 1250. Typically, the hole mobilities are much lower than the electron mobilities. Okay? And the same kind of picture, temperature dependence, applies to the hole mobility too. But I'm not going into that. So what we'll do the next time is to combine all this information together to plot mobility, conductivity versus temperature for semiconductors. Okay? Before that, I've got a couple of things to discuss how the impurity concentration affects the shape, but next time we'll take that up. Thank you.